first PUC topic. So in the previous video we have seen the electronegativity. To include one more important information regarding the electronegativity. As positive charge increases, electronegativity increases. For the same element, the electronegativity does not depend on any other factor except the positive and negative charge. Positive charge. For example, if you consider this Fe plus 3, it is more electronegative as compared to Fe in plus 2 state. Similarly, in hybrid orbitals of carbon, as percentage S character increases, electronegativity increases. Regarding this increase in the electronegativity depending on the percentage of S character, so we will study mainly in detail in the chemical bonding chapter. But you remember, when we consider this carbon triple bond, in this one, this carbon atom is actually sp hybridized. When this sp hybridization is considered, the percentage of S character is 50. Similarly, when you consider this CH2 double bond CH2, percentage of S character, in this case it is sp2 hybridized. Carbon atom is sp2 hybridized, percentage is 33.33. Similarly, in CH3, the carbon atom is in sp3 hybrid state. So, the percentage of S character is 25. So, in this case it is 50. That's why this carbon atom containing this hydrogen is actually acidic in nature because of more electronegative nature of the carbon atom. So, CH triple bond CH is more electronegative than CH2 double bond CH2, more electronegative than CH3. This is electronegativity decreases from CH to CH double bond CH to CH3. So this you have to remember in case of the electronegativity. The next topic is valency. Valency of an element can be defined as the capacity of an element to donate, to accept or to share the number of electrons. The number of electrons shared, lost or gained is called the valency of the element. For S block elements, we know the electronic configuration for the first group is NS1, for the second group it is NS2. Either one electron from NS1 or both the electrons from the NS2 can be lost. Therefore, valency is equal to 1 for the first group and 2 for the second group. For the P block elements, the electrons are present in NS2, NP 1 to 6. The number of valence electrons are varying from 3 to 8. That's why the valency can be calculated as either equal to number of electrons in valence shell, or 8 minus number of valence electrons in the valence shell. For example, for the 13th group elements, that is actually the boron family. The electronic configuration is 2s2, 2p3, 2p1. Either these 3 electrons can be lost or 5 electrons can be gained by this boron. That's why if 3 electrons are lost, it will be equal to 3. If 5 electrons are gained, then it is 8 minus 3, that is 5. Similarly, for the 14th group elements like carbon, it is 2s2, 2p2. In both the cases, the valency becomes equal to 4. If 4 electrons are lost, it gives 4. If 4 electrons are gained, it is valency 4. Either shared or donated or accepted. So, in case of the 15th group elements, 15th group elements have got NH2, NP3. Either 5 electrons can be lost or 3 electrons can be gained. That's why these also show the valency 5 or 3. For example, nitrogen can show from plus 1 to plus 5 oxidation state. That we will discuss in the next chemical bonding chapter. Similarly, for the other elements, we can calculate the number of electrons in the present in the valence shell, or 8 minus number of electrons in the valence shell. It is the topic called as the valency. The next one is oxides. Oxides. Oxides are the binary compounds formed by the combination of that element with oxygen. So, for example, first group compounds can form the elements like MO, M2O. For example, lithium oxide, sodium oxide, etc. Similarly, second group elements can combine with to give rise to calcium oxide, magnesium oxide, like that. So, when we move from left to right, if the elements are metals, metals will form either basic or amphoteric oxides. Amphoteric oxides. Especially in the lower oxidation state, they form the basic oxides. In the other oxidation state, they show amphoteric. Similarly, non-metals will show either neutral or acidic oxides. For example, carbon monoxide is a neutral oxide, while carbon dioxide is an acidic oxide. Similarly, we can consider the various oxides like nitrous oxide, nitric oxide. These are neutral. While nitrogen, dinitrogen trioxide, N2O4, N2O5, they are all acidic in nature. But when you consider these metalloids they form either acidic or amphoteric. For example, we have considered some elements like silicon, germanium, etc. as the metalloids. They will form either acidic or amphoteric oxides. When you have details about these oxides, you will study in the second year, that is 12th standard, in oxygen chapter. That is 16th group elements. The next one is the next topic is hydrides. Hydrides. When an element combines with hydrogen to form a binary compound. Binary compound should contain only 2 elements. When we consider this element A with hydrogen, then it is called as a hydrogen hydride. When you consider these metals, the metal hydrides, they are actually non-volatile with hydrogen as anion. This is called as the hydride ion. Because of the tendency of these non-volatile nature with losing the hydrogen atom, they behave as the reducing agent. Metal hydrides are used as the reducing agents. For example, sodium hydride, lithium, aluminium hydride, they can be used as the reducing agents. While non-metal hydrides, for example, methane, ammonia, they are etc. So they are actually non-volatile. So they are volatile, covalent in nature, and having small molecules. For example, now this metal hydrides, you can take this sodium hydride, lithium hydride, aluminium hydride, AlH3, etc. Now these non-metal hydrides, we can take this as methane, okay, then ammonia, H2S, These are the volatile, they are present in the gaseous state. So they are covalent in nature and they exist as a small molecules. Then coming to the metalloids, metalloid hydrides. These are again volatile, again covalent, and they exist in the small molecules. Small molecules. The last topic in this chapter is the halides. Metal halides, non-metal halides, etc. So when we consider these halides, when an element combines with halosine, it gives rise to halides. When we consider this first and second group halides, first and second group halides, they are exclusively ionic in nature. Ionic compounds. There may be one or two exceptions, for example, lithium chloride. Lithium chloride is a covalent compound. But when we consider these ionic, they are soluble in water, have high melting point, conduct electricity in aqueous solution or molten state. For example, when we dissolve this sodium chloride in water or when we melt sodium chloride, fuse the sodium chloride, it will conduct electricity because of the presence of the ions. Then coming to the ionic character of this one. Ionic character decreases across the period. For example, when we consider this PCl3, that is 15th group element with halosine. This is found to be a covalent in nature. That's why the ionic character decreases. And ionic character depends on the size of the halosine. If ionic character, as the size of halosine increases, ionic character decreases. For example, when we consider the same element like lithium, when we consider this lithium fluoride, it is ionic in nature. But when we consider this lithium chloride, it is less ionic. Similarly, lithium bromide becomes still less ionic, covalent. And lithium iodide exclusively behaves as a covalent compound. So the ionic character depends on the size. As the size increases, ionic character decreases. Okay. So most of the fluorides are ionic. And the size as fluorine to chlorine, bromine, iodine size increases, the ionic character decreases. So this is all the topic on the periodic properties of the elements, classification of the elements and periodic properties of the elements. So we will continue with the other topic in the next video.